2.3 is on linear transformations. This is an important topic we'll see in chapter 2 and chapter 3. So first we define a couple concepts before we get into the actual definition. So first, a function. So we're going to define more of the actual higher level concepts of functions and mappings instead of the typical one you may have seen. So a function f from a set x, I'm using capital, to y is a rule that associates each x in the set x an element y, which we'll call f of x, in capital Y, the set y. We say f maps x into y. And the wording is specific. It's not onto, it's into. Capital X is called the domain, just like we know, is called the domain of f. Then the capital Y is called the codomain. So the range is actually what you normally would define a range to be. The Y is more like the target. So what you have then is you got to set x like this. And then you have, just copy that. You have a set y. And f is, here's your function f from x to y. But the idea is that for the codomain, this is more the target, where you may only use up part of the function. Or I'm sorry, part of the set. So you have a x here, then this is f of x. But depending on the function, you're going to end up having a different subset of y for the range. We'll define that in a second. So a couple things. If you have, so let's just look at an example to explain the next concept. So suppose you had, let's do this, speed up a little bit. Let's go ahead and copy this over. So here's an example situation. I'll just blow it up over here to look at it. So suppose you had f of x is x squared. Then you know that your domain is all reals here. And then when you map f to, so your codomain would be all reals. But we know this doesn't, when you take x and you do x squared, it doesn't end up being all the reals, right? You end up not having the negatives. So the codomain is all reals. That's like your target, which we're going to hit. But your actual values are just here, and those are your positive reals. So this k, this set k, is including 0 to infinity. So that's what your codomain is. And the the image, and I'll define this in a second, we call this here, this part, the image of f. The image is called the range, just like you're used to. When you say what's the range of f, you'll say it's positive reals or non-negative reals. And that's the image of f concept. Okay, so let's define a couple more things. So what you have then is, we're going to let some more ideas here. So let's let H be a subset of the domain X. Then some notation might look like this. If we say F and then of H, the whole set, that is equal to the set F of H such that H is in capital H. And that is, just like we were describing, is called the image of H under F. So it's like doing a domain restriction. So if you have a domain restriction here, we're going to call that H, and then whatever you get on the other side is your image of F under this subset H. Which I have some examples of that below. Okay, so then the image of the domain F, of F, is called the range, just like we would think of F. Then let's look at this. Let K be a subset of the codomain, basically. Then F inverse of K is equal to the set X in X such that F of X is in K. So it's all the values that end up hitting it. So that's the inverse image of K under F. So is the inverse image of K under F. It's like what would map back. So let's look at a couple examples of that. Let's let F be a function from R to R. And I actually picked F of X is X squared like above. Simple one we know. Then let's suppose H is equal to the set 1, 2, 3, and that's all I used. And so H is 1, 2, 3. Then if we said F, little not capital. Then if I said F of that set 1, 2, 3, then we know what that set is. That is the set 1, 4, 9. Now, this is what gets a little squirrely here when you look at the inverse image. What's the inverse image of those numbers? The inverse image is 1, so inverse image of 1, 4, 9 is equal to what? It isn't just 1, 2, 3, is it? It's actually -1, 1, negative 2, 2, and negative 3, 3. So developing some of this new terminology and concepts basically helps us define more rigorously one-to-one functions, what we call onto, when you have a function that maps onto something, like meaning the whole thing. So that's a little later, won't do it a whole lot, but so anyway, the inverse image of f is not just 1, 2, 3. It's all of those numbers. Okay, so a lot of this is just kind of, it'll be used, but not too much yet. So this is called, so f is the inverse image. All right, so suppose you had, so this was another diagram we can talk about. So if you have, let me duplicate that here. We're going to do two diagrams. We're going to call both of these x, and then this one y and y. And so you have in here your set H. Then you have your mapping, your function f, both cases. And so if this is H here, then this set is your f of H. That's your domain. And then similarly, if this is your set K and you go back, then this is the inverse image of H. So this is going back to here, this is going to here. Okay, and they might be different. If it's not a one-to-one function, then you're not going to get this inverse image to be whatever the domain was. And so those are just some concepts we'll look at as we go here. All right, so the next important thing is we're going to look at right now what's called, this is the definition of the linear transformation. So all of that's really just to get some of the terminology and concepts down for linear transformation. So linear transformation is basically a special kind of function. And we want to define that. So linear transformation, we're going to go in this chapter, you're going to call it T for transformation, and it's going to go from Rn to Rm. And so those are your sets. You're looking at vectors to vectors for this chapter, and then we will define this more generally speaking in the next chapter. So this is definitely 2.3, if that matters. So it is a function, first and foremost. And I don't need to redo that. We'll just bring that down. So it's a function. Bring that down there. I just had that earlier. From Rn to Rm is a linear transformation and we will be abbreviating that, as you could imagine, LT, speed things up. if two things hold. So first it's a function, and then one, we have t of u plus v is equal to t of u plus t of v. It's like you can separate the addition. Not always the case, right? I mean, if you look at some easy examples where you can't separate a function out like that. And then 2 t of ru is equal to r of t of u. So you basically can factor out the constant. And that's true, so you can do that, or is true for all u and v in Rn. That's the initial set, which we're putting into the function, and the scalar, of course, r. So r is just a scalar. What if you add those two together, or combine those concepts 1 and 2? We say a linear transformation preserves linear combinations. And so linear combinations would just look like this. You just would be t of, so linear combination of this form, applying both of those properties 1 and 2, you can factor out the r and then get t of u plus s t of v. So you can, that would be a linear combination here, and then you can do this to it. So linear combinations are preserved for this transformation. Okay. So let's look at just a couple simple examples, and then we'll move on to another video. Okay, so first example, let t of x be a transformation, and this will just be from r to r. Where t of x is equal to the square root of x. So is the square root of x a linear transformation from r to r is the question. What do you think? Well, first you need your values in r to be arbitrary. So you arbitrarily let x and y, because you need 2. First you let them be in the set, in the first set, the domain. So now if it's true for those, because they're not specified what they are, they're just some arbitrary values in the domain, whatever happens will be true for all of them. Okay, so then you basically try to show it. So you say t of x plus y, is that equal to t of x plus t of y? And of course, if you don't really show it like that, you just start writing it out. So that's what that means then, is the square root of x plus y. And we know that that is not equal to the square root of x plus the square root of y. Therefore, the square root of x is not a linear transformation. So that's how you would start it to show it. You got to show both 1 and 2, which will be something we do. So therefore, t is not a linear transformation. Okay, so that's what we'll be doing. Let's go ahead and break, and we will do a couple more number of examples after that.